Hi, I'm Diomedis Pinellis and this is joint work I've performed with Maris Frangoulis. We have extended the functionality of the Unix shell to allow the expression of directed acyclic graphs. Here I will show our motivation, the functionality of what we have created, and examples of its use. As you can see from this example of a spell checker created by joining together 6 existing Unix commands with pipelines, Unix pipelines are extremely powerful. The problem with pipelines is that they are linear. I started working on DAGs when I wanted to study the evolution of C programming practices over long periods of time. To do this, I had to repeatedly process the output of some commands with others and then gather together the results. There are 3 alternatives for doing this, however none of them are really satisfactory. To answer this problem, we created DAGs, the Directed Acyclic Graph Shell. Some claim it's the best thing since sliced bread. As an example, consider the problem of comparing the performance of various compression programs. This is the graph of the processing you want to perform. The same data are sent to all compression programs and then the results are gathered together into a single report. And this is how you express it in DAGs. You pipe the output of T to various commands that run asynchronously within a multipipe block. The block is enclosed within a double opening brace and a double closing brace. Commands running before the block can pipe their output to multiple commands within the block, and commands piped from the output of the block can receive input from multiple commands. DAGs introduces 3 inter-process communication ways: multipipe blocks, Unix commands that can have multiple I/O channels, and also stored values. To take advantage of DAGs' multipipe capabilities, we adjusted the number of Unix programs to allow them to take multiple inputs and produce multiple outputs. For example, the com command can take as input 2 streams and produce as output 3 streams, the records occurring in the first stream, the records occurring only in the second stream, and the records occurring in both streams. An application programming interface allows programs to specify the number of inputs and outputs they support. A wrapper program allows existing programs to work within DAGs with minimal fuss. Let's see some more examples. Here is the awkward backward and forward data flow associated with Bash's process substitution mechanism. The same can be expressed much more elegantly in DAGs with a multipipe block. You can find duplicate files within a directory hierarchy very efficiently by joining duplicate MD5 sums with the corresponding file names. You can analyze Git repositories by sending the output of Git log to multiple processes. In this case, we find authors and days ordered by the number of their commits. Here is the result of running the program on the Linux kernel. To highlight misspelled words, the original text is combined with the misspelled words. This is done by nesting multipipe blocks. Here is an example of the command's output. You can find C/C++ identifiers that should have been declared static by looking at those that have been exported and never used. This is what I get when I run this program on the bash object files. The list of possible applications goes on and on. DAGs has been used for weblog reporting, for processing data with 2-dimensional Fourier transforms, for performing nuclear magnetic resonance processing, for running parallel fast Fourier transform computations, for distributed processing using the split combined paradigm, and for combining separately drawn diagrams. We encourage you to download DAGs from its GitHub repository and use it for your own processing. You can also package it for your favorite operating system distribution, adapt existing tools and develop new ones, and contribute enhancements and bug fixes. Many thanks for your interest in DAGs, the Directed Acyclic Graph Shell.